Welcome to this explainer where we're going to completely demystify green engineering. We're taking it from a visionary, feel-good buzzword and turning it into a concrete, systematic framework for our future. We hear the word sustainability thrown around constantly today, right? It's plastered all over consumer packaging, it's bolded in every corporate mission statement, and it echoes through these massive international treaties. But having a grand vision is very different from actually building that vision into reality. So why should we care about a foundational framework from 2003 right this second? Well, because we're at a tipping point. The climate crisis and resource depletion are moving way faster than our current industrial solutions. Today, we're going to use the foundational design through the 12 principles of green engineering to fundamentally change how we think about the materials, products, and systems we interact with every single day. This isn't just about feeling good. It's about the hard math and science of redesigning our modern world from the ground up so that it can actually survive.
But first, we really have to ask ourselves a crucial question. Is setting a green goal actually enough? We all want sustainability for sure, but simply setting a goal to reduce waste or recycle more often falls drastically short of solving the actual problem. Setting a goal is just an intention. It's not a mechanism. Think about it. You wouldn't expect to build a towering 100-story skyscraper just by declaring your intention to have a really tall building, right? You need a rigorous blueprint, structural engineering, load calculations, and precise execution. The exact same logic applies to saving our environment. Just wishing for a cleaner planet without changing the fundamental physics and chemistry of how we manufacture goods, that's a total recipe for failure.
All right, let's kick things off with Section 1, the sustainability gap. So, there is a desperate need for a bridge between our abstract sustainability goals and practical systematic engineering implementation. The source material argues that without a systematic and scalable approach, our big environmental visions are essentially just wishful thinking. We've spent decades outlining exactly what we want to achieve, cleaner air, less toxic waste, sustainable resource use, and a stabilized climate. But the engineers, the people actually designing the molecules in our medicines, running the factory floors that build our cars, and creating the consumer goods filling our homes, they need universal design parameters to make those goals a physical reality. When this scalability is missing, we end up with these isolated one-off green projects that look fantastic in a press release but do absolutely nothing to move the needle on global emissions or waste. Engineers need a systematic way to implement these ideas at a massive scale. They need an operational blueprint that turns philosophy into physics and good intentions into commercial viability. That brings us to Section 2, the power of inherency. Inherency means using materials and processes that are non-hazardous and benign by their very nature. Think of it exactly like baking. You literally cannot bake a cake with toxic ingredients and then try to somehow extract the poison later. You have to use safe ingredients right from the start. For a long time, the traditional industrial approach was to just use whatever dangerous chemicals, high-pressure systems, or extreme energy processes got the job done the quickest and cheapest. Manufacturers would then just sort of figure out how to handle the inevitable toxic byproduct later. Green engineering flips that entirely on its head. It demands that the starting materials and the core processes themselves are inherently safe, because if the foundational building blocks are harmless, the risk to human health and the environment drops to zero, regardless of what accidents or failures might happen down the line. And this brings us to a really stark contrast: circumstantial control versus inherent design. This proves that true sustainability is proactive, not reactive. Circumstantial control is exactly what it sounds like. It's putting a Band-Aid on a toxic process to manage the mess. It's installing a massive, highly expensive scrubber on a factory smokestack to catch airborne pollutants before they hit the atmosphere. Or it's requiring workers to wear heavy hazmat gear because the chemicals they're handling are inherently lethal. Inherent design, on the other hand, means re-engineering the entire manufacturing process so there is absolutely no smoke to scrub in the first place, and zero toxic chemicals to endanger the factory workers. It's about designing safety and sustainability into the very DNA of the product, totally stripping away the need for constant, costly vigilance. Okay, let's jump into Section 3, life cycle thinking. The second foundational pillar of these 12 principles forces us to expand our timeline. It requires us to look at the entire lifespan of what we create through life cycle design. This means considering the environmental impact of a product from cradle to grave, encompassing its entire existence. We can no longer just think about the product while it's in the consumer's hands. Historically, a product's design was considered a massive success if it worked well for the buyer and was cheap to produce. But ignoring the grave aspect, what actually happens when the product dies, has led straight to our modern environmental crises.
We're talking everything from literal mountains of e-waste to microplastics floating in our oceans. Green engineering demands that we look way beyond that brief window of utility and take real responsibility for our product's ultimate destiny. To truly practice life cycle thinking, engineers have to account for the environmental cost at every single one of these stages. It starts with extraction, pulling raw materials out of the earth. How destructive is that initial footprint? Are we strip mining a forest just to get the metals we need? Then comes manufacturing. How much energy and fresh water are being gobbled up to turn those raw materials into a finished good? Next is the consumer use phase. Does the product require constant, massive amounts of electricity just to run? And crucially, end-of-life separation and recycling. What happens when the product breaks or is simply no longer needed? Listen, if a product works beautifully for a single year but then sits in a landfill leaking heavy metals and toxic chemicals into the groundwater for 1,000 years, that is a catastrophic failure of engineering. Now, we can chunk these 12 principles into highly actionable themes that integrate environmental, social, and economic factors right from the start. Instead of memorizing 12 separate, isolated rules, consider these practical applications. Waste minimization is an obvious starting point, but take output-pulled systems, for example. This means designing manufacturing processes that only produce materials as they are actually demanded by the market, rather than overproducing and storing massive inventories of hazardous chemicals that could leak or degrade. Then there's targeted durability. Basically, we shouldn't engineer a disposable coffee cup to outlast the Roman Empire. Its lifespan should match its use. And minimized material diversity, alongside design for separation, means making products out of fewer, easily separable components. A smartphone should be easily disassembled so its rare earth metals can actually be recycled, rather than ending up as a permanent, fused block of unrecyclable plastic, glass, and toxic glue.
Which brings us nicely to Section 4, designing across all scales. So, where exactly do we apply these principles? Are they just for giant industrial factories, or maybe just for specialized chemists in a lab? The reality is, they scale perfectly across every single level of design. At step 1, the molecular level, chemists can engineer the actual molecules of a pesticide to degrade safely into harmless dirt the very moment it finishes its job, rather than persisting in the food chain. At step 2, product engineering, designers take those benign materials and engineer a laptop or an automobile that is modular. That means you can easily swap out a broken battery rather than tossing the entire machine. And at step 3, systems-level applications. Urban planners and industrial ecologists can design entire supply chains, transportation networks, and regional power grids that operate on these exact same closed-loop principles. The absolute beauty of this framework is its universal adaptability, from the microscopic all the way to the global. Finally, let's look at Section 5, redefining our systems. This brings us to the ultimate realization of what this framework is truly demanding of us. Green engineering requires us to rethink our entire approach to industry. We simply cannot settle for just making an unsustainable system slightly less bad. We must redefine the system entirely. Optimizing the unsustainable is a really dangerous trap. It makes us feel good while changing absolutely nothing fundamental. Let's say you have a massive textile manufacturing process that uses a highly toxic solvent to dye clothing. If you spend millions of dollars and years of research to make that process 10% more efficient so it uses a little less solvent, well, you are still ultimately relying on a highly toxic chemical that endangers workers and pollutes waterways. You've just optimized an unsustainable system. Fundamentally redefining it means throwing out the old playbook entirely and engineering a completely new process that uses pressurized water or harmless natural enzymes instead. It is a total shift in how the problem is solved. Transition from optimizing unsustainable systems to fundamentally redefining them for inherent sustainability. This quote captures the ultimate essence of the 12 principles. It is a complete systemic paradigm shift. It's a bold declaration that doing less bad is simply not the same thing as doing good. A slightly more efficient toxic process is still a toxic process. Green engineering is not a supplementary add-on, it's not a marketing gimmick, and it's definitely not an afterthought applied at the very end of an assembly line. It is a fundamental reimagination of how humans create and sustain the built environment. Ultimately, understanding these 12 principles leaves us with a really powerful question. If everything around you was re-engineered using these principles today, what invisible hazards would simply cease to exist? Think about the phone in your hand right now. Think about the synthetic fibers in the clothes you're wearing, the paint on the walls of your house, and the packaging your food comes in. If all of that was designed for true inherency, with deep life cycle thinking and built for targeted durability and rapid separation, how radically different would our world look? We wouldn't just be managing a global environmental crisis, we would be literally designing our way out of it. Understanding this framework gives us the lens to see not just the monumental problems we face, but the exact systemic engineering blueprint required to solve them.